Hello, and welcome to our presentation on our computational geometry project, where we are examining the flip graph connectivity of plane-spanning paths. My name is Kelly.
I'm Mansi.
Let's get started. So the general class of problems that this falls within are reconfiguration problems. So reconfiguration problems ask questions about the transformation of objects by small local changes. So these are going to be the smallest atomic changes by which you can take one object in a class and transform it into another object in the same class. These are called flips. A flip graph captures the structure of a particular reconfiguration problem so that all particular configurations, as you can see here, triangulations of a pentagon, are vertices in this graph, and flips are represented as edges. So two vertices are adjacent if they can be flipped to each other.
On a set of given a general set of points S, a plane spanning path is a path that has the following properties. All vertices in that path have degree less than or equal to 2. No edges intersect each other in the given plane, and P has no cycle.
So essentially the definition of a graph theory path, but with the additional requirement that there's no intersection of edges. A flip in a plane spanning path is defined as adding an edge between one or more endpoints and another vertex in the path, and removing an edge. So a type 1 flip is an operation that adds an edge between an endpoint and some visible vertex, and then removing the first edge on the subpath between that vertex and that endpoint. So you can see here we add this edge, we remove this edge. A type 2 flip is where we add an edge between the endpoints if they are visible to each other, i.e. there are no edges crossing this, and we can remove an arbitrary edge. A type 3 flip is a sort of a special kind of type 2 flip where if there is only one edge intersecting between both endpoints, we choose that intersecting edge as the edge we will remove during our flips. So you can see here we remove the intersecting edge.
The conjecture is that flip graph for plane spanning paths is connected. Currently, it is known for some special point sets with some special geometries, which are point sets that are convex layers, point sets that are convex polygons, point sets with no more than 2 convex layers, generalized double circles, and wheel sets. Right? Given that any point set can be decomposed into multiple convex layers, we do think this is an essential result because everything is about with respect to convex hulls. So we first discuss one method which is used in Kleist et al. To extend the K-layer property to 3 layers, right? So given a point set in a general position with multiple convex layers, the goal is to prove connectivity of flip graphs of plane spanning paths via induction on those convex layers. So the strategy is to reduce an arbitrary path to a suffix independent path, because Kleist shows that suffix independent paths have connected subgraphs. So K-layer property is for paths which are chord free and whose first edge leaves L0, right? L0 being the layer, the outermost convex layer. So the K-layer property states that given a path which has fewer than L0 minus 1 level edges, there exists a flip to another path such that the level edges are either increased or they remain the same with the new endpoint of the path being on that level edge, right? So this means that the flip structure strictly increases the convex hull structure or moves an endpoint to an outer layer. Repeated applications will help you prove for multiple convex layers. So at k equal to 2, the two-layer property holds. It is proved by Kleist et al. The proof structure is as given there. There are two phases, and it handles three different kinds of obstructions, and local flipping via convex regions is dealt with by lemma 14. This is the current structure of lemma 14. We extend that to add additional layers and use that to extend k layer property to k equal to 3. So this is our modified lemma 14, right, where given a suffix independent path and a spanning for a specific subset of S and a given specific edge, we assume that the edge is on the boundary of their convex hull and the region contains no points of L0, and that there is a specific internal convex region containing called W, and we use induction on A and W to prove modified lemma 14, and we use that to prove for k equal to 3, and there are 3 current layers and the obstructions that we're dealing with remain the same.
The other approach we took towards proving whether or not the flip graph of plane spanning paths is connected is through the partial ordering of paths. We can approach the problem of flip graph connectivity by imposing organization on it. So if a flip graph can be ordered, then we have a notion of direction, and we can define an optimum as a sort of fixed point where we want to always flip towards. Let's see here. So this was inspired by reverse search for enumeration by Avis and Fukuda. So Avis and Fukuda apply such an ordering to Euclidean spanning trees, and by doing so they're able to prove that a given tree can be flipped to their defined optimum. And since plane spanning paths are a restriction on Euclidean spanning trees, we can derive that the flip graph of plane spanning paths is a subset of the flip graph of Euclidean spanning trees. We define an optimal path as a spiral, counterclockwise spiral around the convex shells, where the first vertex of P star is blue, last vertex is green, and we order the points by their position in this path. For Euclidean spanning trees, we can take an edge from the optimum and remove an edge from a non-optimum and put those together, and the resulting structure is also a Euclidean spanning tree. But as you can see here, there are counterexamples to this for plane spanning paths. So we needed evaluation that a way to add edges that was less restrictive. So we kind of determined that the valuation can't be based on the position of vertices because a flip can reorder up to n vertices. So we define our valuation as corresponding to the angles between for a given point pj, we define theta to be the angle between the point it is adjacent to in the optimum and the point it is adjacent to in the non-optimum. And we are able to compare these by looking at which of the points it is adjacent to in the non-optimum come first. Angle of P only changes for those points whose neighbors change after a flip, and we were able to identify these. And since this valuation only changes for those local vertices, we can conclude that ang of P is a good candidate valuation for plane spanning paths. We don't know that if ang of P gets better, that P prime is closer to the P star. So we conjecture that there exists a path through there exists a sequence of flips through a more non-optimum path that so we conjecture that there exists a sequence of flips from two local minimums of ang of p through a path that has a greater valuation. And through this, we believe that it can be shown that the flip graph is connected. Sort of traversing between local minimums until we are able to get to the global minimum of p star. We weren't really able to observe immediately that how ang of p changes as flips happen. So we did an experimental study on vertices of a square and a polygon, and we found that the change in theta for the endpoint is predictable. We're sort of optimizing towards the topmost vertex. And we also found that the same applies for the vertex in a flip for whom the number of neighbors does not change. So this would be VI.
Given that we've proven the three-layer property, it is not as simple to say that convex layers, for up to 3 convex layers, flip graphs are connected. While this is still the center of the flip graph, we cannot directly say that as easily as we could at k equal to 2, because k equal to 2 has planarity on its side, right? We have visibility constraints that we'll need to deal with in a later case, which will then extend k equal to 3-layer property to all of 3 convex layers. Further, for greater than 3 layers, our inductive step has moved from the suffix independent path in lemma 14 to an internal convex layer, right? And we look at growth in that convex layer to prove for further cases, and then we'll need to tweak lemma, the 2 and 3 conditions of lemma 14 accordingly to account for visibility.
We believe that the angle evaluation will be a useful tool for further looking at flip connectivity for plane spanning paths. In our current understanding, how and when ang of p changes is dependent on the geometry of the input point set, and flipping for the greatest decrease would require checking every candidate flip, every possible flip. And because of this, this sort of hints towards deciding flip graph connectivity for a given point set is difficult. It could be intractable. And if this is the case, where ang of p is strictly dependent on the geometry of the input point set, we believe it could be used to show that deciding flip graph connectivity is hard for arbitrary point sets. So we will be looking in the future and trying less to prove that it is connected, and more trying to examine whether ang of p implies that deciding flip graph connectivity is a hard problem, an intractable problem. Thank you. Thank you for watching our presentation. We hope you've learned something, and have a good day.